At the age of 17, Newton wondered why an apple falls from an apple tree, while the moon does not fall to the earth. Until that time, people thought that objects on Earth, such as apples, did not follow the same laws as celestial bodies. Comparing the motion of the moon and an apple, and thinking that there might be universal physical laws valid on Earth as well as in the skies, was a revolution. Before Newton, physics was dominated by the thoughts of Aristotle. Aristotle suggested that each object had its proper place. If we move it from that place, it will do its best to return to it. Everything around us seeks its natural balance. An apple tends to go down, since that is its nature. The moon orbits the Earth because that is its nature. In fact, understanding falling objects is not so easy. By the way, folks in cartoons also have problems with physics. Here is the first law of physics in cartoons. Any object suspended in space remains motionless until it becomes aware of the situation. And according to a cartoonist at Disney, cartoons follow the laws of physics, unless the opposite is funnier. Newton came up with a universal law of gravitation. Two bodies attract with a force proportional to each of their masses and inversely proportional to the square of the distance between them. Where does this force of attraction come from? How can it be explained? How can two objects, separated by billions of kilometers, attract each other seemingly instantaneously? This mystery was not explained until much later, and only in part, by Albert Einstein. All objects, an apple as well as the moon, are attracted by the Earth. The force of gravity affects everything that surrounds us. Another great idea from Newton is that forces modify speeds. When a speed increases, we say that the object accelerates. So, imagine an apple affected by one force only, its weight. In the vicinity of the apple tree, gravity is essentially constant. At the moment that the twig breaks, the apple has speed equal to 0. But the force of gravity changes the speed. The apple falls faster and faster and crashes to the ground. Newton goes further. He explains how, if we know the forces, we can calculate a trajectory. Here is a ball rolling on a plane. What will happen to it? Nothing. It will continue to roll at a constant speed. This statement, found in physics books, is true, naturally. except in that it does not match what we observe in day-to-day life. A billiard ball will eventually stop because frictional forces slow it down. But let's ignore those forces. When the ball is in contact with the ground reacts and applies a force in the opposite direction, preventing the ball from piercing the ground. So the total force acting on the ball is 0. If there is no force, there is no change in speed, and so the speed remains constant, as we have seen before. However, when the ground gives way, the ball is still subject to the force of gravity, that is, its weight, which now changes the speed. This is because there is no ground left to counteract the weight. Newton expressed all of this in one of the most important formulas of physics. F equals ma. F is the force, m is the mass of the object, and a is the acceleration. The acceleration is the rate at which the speed changes. In other words, the derivative of the speed. In our situation, the force of gravity is constant, directed downwards. So the acceleration is constant and directed downwards. The velocity vector will increase every second by the addition of a constant vector. Look at the trajectory. It's a parabola. If we know the forces that are applied to a system, we know the acceleration. If we also know the initial position and the initial speed, we can then predict the future movement. If you aim very well, and if you choose the right initial conditions, you can get incredible motions. An initial condition is not just an initial position, but also an initial speed. Look here. We have 3 planets without a sun following 3 closed trajectories. The motion is periodic. Here things are more interesting. The 3 planets share the same trajectory. And here, the 3 planets also follow the same trajectory, a figure of 8. This is a planetary dance. It must be said that such an elegant ballet is difficult to choreograph. In order to arrange it, we have to aim very well, as in billiards. If we change the initial conditions just a little bit, wham! The beautiful choreography turns into chaos. By the way, if the moon is really attracted to the Earth, the way an apple is, why doesn't it fall to the Earth the way an apple does? Newton's answer is amazing. It does fall. If we observe what happens in the vicinity of the Earth, the force of gravity is not constant. It is always directed towards the center of the Earth and is less and less strong as we move away from the Earth. The Earth attracts the Moon by a gravitational force which influences its trajectory. However, because this is combined with a rotation, the Moon is constantly falling and never reaching its goal. If the Moon were not subject to any force, it would move in a straight line, ignoring the Earth completely. So let's take a fictitious moon at 384,000 kilometers above the Earth and let it loose. It falls. Second attempt. Let's launch the same moon with a small initial horizontal speed. The trajectory deviates slightly, but we have not avoided the catastrophe. With a higher initial speed, the moon misses the Earth narrowly and continues turning around it periodically. A higher speed yet, and the moon rotates on a circular orbit, more or less what happens in reality. Too high a speed and goodbye moon. The solar system has 8 main planets and thousands of secondary objects, all interacting with one another via gravity. In the study of such a system, the description of the initial conditions will involve many positions and many speeds. And just imagine all the data necessary to describe the motion of the atmosphere with its countless molecules. Studying the trajectories of a vector field that depend on a large number of variables, this is the real challenge launched by the great Newton.